All right, hello and welcome back to the probability slides. Let's finish these up. So last time we were talking about, towards the end, we were talking about conditional probability, the probability of like event E given that we know event F has also occurred. This is what it's defined to be, and sometimes that can tell you a little bit more. If you know that F happened, that kind of changes what E might do, and that might give you a better, more accurate probability for it. Sometimes it doesn't change anything at all, and that's when those two events were independent, and so we talked about that. But along those lines, let's say we know these three things. I know the probability of B given A, and the probability of A by itself, and the probability of B by itself, but honestly, I want none of those. I'd really, really like this instead. I really want to know the probability of A given B. That's what I'm really after. It turns out that these three can create this for you, surprisingly. And here's the formula. It's called Bayes' theorem that gives us this formula. Bayes is a dude's last name. And let me prove that to you. If I have this, if I have the probability of B given A, how can I use that to get the flip side of that, probability of A given B? So if I have this, if I know I have the probability of B given A, what's that equal to? That is probability of A intersect B over the probability of A. That's always the thing last. Kind of like a slash. This is like a, kind of looks like a fraction almost, and that's how you can remember it. And we can solve this for the intersection, and that's going to be important because that's the thing that these two share, right? If you use that formula to calculate those two conditional probabilities, they're going to share that intersection. And so that's helpful. So this is equal to the probability of A times probability of B given A. If only I could write a B. And we multiply that, or we already did. That's equal to the probability of A intersect B. Okay, that's cool. We got that. So that's the most important part. And watch what happens. We need, right? We need the probability of A given B. That's what we're after. A given B. And that looks like two parentheses, sorry. A given B. And we know by the formula that that is equal to the probability of A intersect B over the probability of just B. And hey, I just found a way to get at the probability of A intersect B. It's this thing. Just put that there, and then divide by the probability of B. So if you have those three other things, that will give you the other conditional probability. That's really cool. All right, so that's Bayes' theorem. That gives that to us. Honestly, you don't even need the probability of B. If for some reason you don't know the probability of B by itself, but you do know this other conditional probability, the probability of B given A bar, be given that A is not true, that will let you actually calculate the probability of B by itself, given those other things that you have. So it's assuming like you still have this and this, but you also know this. Instead of probability of B, you can solve for the probability of B. And here's how. It's equal to this times this plus this times this. The probability of A bar is, of course, 1 minus the probability of A. You have that immediately. So let me show this to you. So let me prove that to you. What is this? What is this equation? This is B given A, probability of B given A times probability of A. That's this all over again. That's probability of A intersect B. And then what is this then? Along the same lines, this is going to give you the probability of A bar intersect B. Interesting. And it just so happens that is equal to the probability of B. Let me show that to you. So like here's A, here's B. They may have some overlap. I don't know. There might be some overlap. These two actually add together to be all of B. Let me show that to you. So this is A intersect B. That's this stuff. That's this part. Cool. I'll draw that in there. And then, let's see. Then the probability of A bar intersect B. So what's A bar? It's everything outside of A. It's like all this stuff. It's out here too, right? it's all this stuff here as well that's in B, but it's everything else too. If I intersect that with B though, ooh, that's when I get this cross-marked stuff, let's say, checkered stuff. And that is exactly the part of B that's not in A. You see that? So like the part of B that's in A plus the part of B that's not in A makes all of B. So that's cool. So if you know this other conditional probability, but you don't know the probability of B, you can obtain it, believe it or not, which is fun. So that's Bayes' theorem. It's very helpful because usually it's nice to be able to flip things like this. And that is how you can do it. So the world's most standard example of using Bayes' theorem and to show how useful it is it has to do with like illnesses and like testing for illnesses. So think of it like a COVID test or something. And we want to figure out how good a test is for some illness. Let's say that we make our own COVID test or something and it's 90% accurate when somebody has the illness. So writing that within conditional probabilities, it's like the probability that your test was positive given the person really did have that illness is 90%, 0.9. All right. Let's also pretend that the illness only happens in 5% of the population. So the probability that a random person you pick off the street has that illness is 5%, which means, therefore, that the probability of not having the illness, of has illness bar, is, or probability of no illness, is 1 minus that. So 95% chance just a random person you pick up off the street does not have the illness. All right, let's keep assuming things, and we're going to eventually use Bayes' rule. So suppose that our test is only 80% accurate when somebody doesn't have the illness. So the probability of the test coming up negative, given that the person did not have the illness, is 0.8, 80%. And that means the probability that was positive, that it was a false positive, it was positive given that the person did not have the illness, is the opposite of this. It's 1 minus that, so 0.2, 20% chance. It gave you a positive reading even if the person was healthy. And so now, with all these things taken together, we have the things that we need. What is the probability that somebody has the illness when the test gives back positive? Because this is what we really care about, right? What is the probability that I get a positive test, or what is the probability that this person has the illness really, 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 given that the test was positive? Do you see how that's probably the thing you really care about as the test maker? This is not as useful to you. You want the flip of that. And the way you can get it is using Bayes' rule, this idea. Probability of B given A times probability of A over the probability of B. And well, let's do it. So this question marks, these are all equal to probability that has illness given positive is the probability of the flip side, right? Probability of the opposite times the thing on the right. Probability of positive given has illness, let's call it high like that, times the probability of has illness over the probability of positive, which we do not have. It's not here, but we can get it. We can calculate that by these ideas. This thing down here, because we have these two conditional probabilities, which is nice. So if we just plug all that in, it's going to be the probability of positive given has illness. So we want the probability of positive. And that's times the probability of has illness. And then we want to add that to the probability of positive given has illness bar, which is no illness. And multiply that by the probability of no illness. And those are the things we all have, apparently. And that will give us our answer. And so that's going to be, let's see, that probability of positive given has illness, that's 0.9. So let's do the scratch work over here, I guess. 0.9 times probability of has illness is 0.5, or 0.05, sorry. All that over 0.9 times 0.05 plus positive given no illness. So that's this one, that's 0.2 times probability of no illness, that is 0.95. And if you do the math, this is about 19-ish%, so 0.19, and that's your answer. The probability that somebody actually has the illness when you get a positive test back, all these numbers look nice, like 90%. It's a pretty good negative result as well. But honestly, because the illness is so uncommon, it only happens in 5% of this population. Even if it comes back positive, it doesn't really tell you much about if that person had an illness. Unfortunate, which is a pretty bad test, believe it or not. So that's what statistics can tell you. Things that seem a bit paradoxical, like that. So that was a pretty bad test. Probability of you actually having the illness, given that the test gave back a positive reading, was 19%, and they should do better than that. All right. So that is a good example of Bayes' rule. Next, let's talk about random variables. This is kind of like I like to think of this as like a computer science concept. It's like a function call almost, and something weird is happening, and like there's randomness involved. But so it should kind of make a little bit of sense, given that we are programmers. This is a mathematical concept, though. It's called a random variable. A random variable, you give it a name, usually a capital letter. Let's say that a random variable x. All it is it's a function. It's a function from your sample space of your experiment, like the numbers on a die, or like the numbers on one of these little turny, spinny things. So it's a function from that, from a sample space, to the real numbers. So like just a number, whatever number you want to assign to this outcome. And so yeah, it's essentially a variable that if you look at it, it's like it has a different value, something like that. Like you look at it, it's random. It could be 1 right now. If you print it out later, it might be 2 later, something like that. That's how I think of it. And then, so honestly, it's really a function, and we use this notation to talk about the range of that function, like what values could it give back given anything in the sample space. So it's like we can call it with the entire set, and it like gives back everything that it could give back. And so that's what a random variable is. This will make much more sense with an example. All right, so here's a good example from your book. Let's make a random variable d to represent rolling 2 dice. So I have 2 dice that I could roll, and here's like 2 possibilities of me rolling them. I've got a blue die and a red die, and we want to assign a number to each outcome. That's important. That's what random variables do. They're always going to the real numbers somehow. So we'd like to assign a number to each outcome, and let's have the number that we assign to each outcome be the sum of the numbers that are on the dice. So for example, if we rolled it like this, the value of our random variable would have been 9, because that's the sum. But if we rolled the dice this time, the value of our random variable would have been 5. You see how it changes depending on the outcome. But we're giving a number to each outcome. That's important. And then we want to think about the range. Or I guess let me show you an example of this. So here's an experiment E, and our random variable's d. Given that this experiment happened, what's the value of our random variable? It's the sum of the dice in experiment E. It's the 5 plus the 4. It's 9. Okay, so that's kind of how you write the notation. And then finally, the range of that entire random variable d is just all the different numbers that you can get back by rolling 2 dice. Well, you can get snake eyes, 2, a 2 and a 1, or a 1 and a 2. That gives you 3, all the way to 2 6s, which gives you 12. And you can get anything in between. So that's the range of the random variable. That's all the numbers that it could take on if you inspected it, and it gave you back some random dice roll. Okay, that's kind of how I want you to think about it. Another example is like you have these spinner things that could land on 1, 2, or 3, and you spin them. And let's say that we make a random variable called m, and that's supposed to be the sum of these 2 spinners. So we take them as one big chunk of two spinners total, and we spin them, and this is a particular outcome. This is like the blue spinner ended up on the 3, and the red spinner ended up on the 2. And again, we have to assign a number to each outcome. So like the number that we'll assign with our random variable m to the outcome 3, 2 will just be like the sum of those 2 values, which is 5. So that's all a random variable is. It's an interesting little concept. It's quite powerful though. So that's a start at least. It's just assigning a number to each outcome, and like what are all the numbers it could take on. All right, let's keep trucking. You can have a distribution for each random variable. It's like what does it take on? What are the probabilities that it takes on each thing? So the distribution of a random variable is just, it's a set of pairs where like r is a value that the random variable could take on, and then you list that with the probability that the random variable ends up being that value. So the example will help this make sense. And it's just the probability of each number in the random variable occurring, the probability of each value of the random variable occurring. So like here's m again, our random variable m, and like for each outcome we can count how many ways it could happen. Like for example, there's only one way to get 2, because that's when the spinners both land on 1. There's only one way to do that, and there's nine different possibilities total, as we'll see. Like the blue spinner could have been a 1, and the red spinner could have been a 1, and that's the only way to make a 2. All right, we'll get back to the 9s in a second. So like this is the only way. That's the only event that causes the random variable to be the 2 when the spinners are 1 and 1. There's 2 ways to make the 3 though. It's like the blue spinner could have been 1, or the red spinner was 1, and then the other's the 2. So that sums to 3. Those are the 2 ways to make 3. There's 3 ways to make 4, 1, 3, 2, 2, or 3, 1. 2 ways to make 5, 2, 3, and 3, 2, and then 1 way for the spinners to make 6. They both have to land on the 3. And so then you can add up all these things. It's like, all right, what's the probability that all these happen? There's apparently 9 different outcomes total, and so like this is just 1, so it's 1/9 chance you get that value of the random variable, 2/9 chance you get this value of the random variable. That's all what's going on. So this is m equals r. So like this is when the random variable is equal to 2, this is when the random variable is equal to 3, this is when the random variable is equal to 4, and so on. That's the distribution of a random variable, and you can talk about the probabilities behind it all. And then finally, the most important thing usually that you want to do with a random variable is figure out what is the value that I should expect. What's the expected value of a random variable? Like if I do this enough, if I inspect this random variable enough, and I like average together everything I see, what is the average value I should expect to see when I like turn over this random variable rock and look underneath it and see what's actually there? All right, so that's what's going on, and the notation for that is e, and then the random variable's name in brackets, so e of x, for example, the expected value of the x random variable. All that is it's a weighted sum. It's just a weighted sum of like for each outcome in the sample space, it is the value of the random variable for that outcome times the probability that it would have occurred. Okay, that's one way to think about it. It's just a weighted average. That's all it is. Alternatively, you can think of it as if you get the probability that the random variable ends up on this value, if you calculate that, then you just multiply that by each value that it could take on and range over each one like that. That's going to give you the same answer. It's just a weighted average of all the different possibilities to give you the number that you should expect to see. And hopefully that is intuitive once I give you this example. Let's see here. So for example, for this guy, it's like, what is the expected value for this random variable m, which is like the sum of those 2 spinners? What is the expected value for all these things? So it's going to be, you can do it this way. This is the easier way. Once you have this calculated, it's all right, the value of the random variable times the probability that it was 2. All right, plus, it's a weighted average. 3, because it could have been 3, and then the probability that it ended up being 3, plus. So that's that one, plus that one, plus, well, it could have been 4, and there's a 3rd chance it was 4, plus. Could have been 5, and there's a 2/9 chance it was 5. Could have been 6, and there's a 1/9 chance it could have been 6. And so you just add up all those things. It's a weighted average, like the 4 has a 1/3 of the weight, a 5 has a 2/9 of a weight, and this comes out to be exactly 4, surprisingly, which is pretty cool. And so that tells you that if you look at this random variable, it's going to give you a random value each time. But if like you look at that random variable 1,000,000 times and you like average together all the different values that you get, you can expect to get on average the number 4. That's kind of what this is saying, and that's the number you should hope to get, essentially. That's what's going on. You can also do conditional random variable expectations. It's like, what's the expectation of the random variable m given that we know that the blue spinner landed on the 1? You can totally do that, and here's how you calculate it. It's like, all right, where are all the ways that the blue spinner was a 1? It looks like these are the 3 ways. And you do it all over again. Like, what's the value associated with this outcome? It's the 2 times what's the probability that we ended up with this outcome given the outcome, given that we know blue is 1. And so there's really only 3 options now. Only 3 possibilities, and well, it could have been a 2 with a 1 out of 3 chance, because there's three ways for the blue spinner to be a 1. plus, well, it could have been a 3. There's one way when it's a 3, and it's 1/3 chance that it ended up like that with the blue spinner. A 1, but the 2 this time. 3 times 1/3 plus, also could have been a 4 with another 1/3 chance. I hope you see that. 4 times 1/3, and I think you can imagine that this answer is 3. The expected value of the random variable, given that blue ended up 1, is 3. On average, you can expect to see to obtain a 3 if you look at your random variable. All right, so that's the expectation of a random variable. That's the most important thing, pretty much, that you can do to a random variable once you make one. All right, and so here's a question for you. Here is a little experiment. Let's say that we make an experiment where a red die and a blue die are thrown together. So we got 2 dice, one's red, one's blue, and let's make a random variable to associate everything. So let's let x be a random variable whose value is the product, not the sum this time, but the product of the numbers on those 2 dice. Okay? So I'd like you, I guess you can use my answer to cheat, but I'm going to write a program for you I'm going to show you a program that does this. But I encourage you to write your own and just look away from this right now. But I want you to answer these things. What is the range of this random variable x? I encourage you to write a program to help yourself. I'll show you mine in just a second. Then give the distribution of that random variable x. And then finally tell me what's the expected value that I should expect to see if I rolled this red die and blue die together. What's the expected value that I can see that's the product of those numbers? What can I expect? Okay? So that is that. So give that a try. And so, for example, like if your dice have the values, like the red one was 2 and then the blue one ended up on a 3, like the value of the random variable in that case was 2 times 3, so 6. Okay? So that's the idea there. And so that's the kind of thing that I want you to be thinking about. All right, so this kind of gave away a little bit of the answer. Let me show you how I wrote this, because I want you to do the same thing. Let's see here. So this is just going to be a loop. This is a loop in Racket. I'm going to keep track of every outcome, and I'll make a hash table of all the counts and things. But I is going to be the first dice, or the first die. It can range between 1 and 6, and it's going to be a nested loop. J is the second dice, the blue die, and it will range between 1 and 6 as well, because that's what you can get on a die. And the event is that roll, essentially, but the value of the random variable is the product of those 2 dice. And we're going to keep track of the number of rolls, the number of different outcomes. It's 36, of course, and the number of different ways that we can do things. It's 36, and then I add 1 to the count of whatever product we found. So if we found a new way to make 6, I'm going to add that to a hash table, and like there's a new way to do it. I'm going to keep track of how many ways there are to make that particular value in a hash table, and then I will compute the expected value based on that. So let's see here. The expected value is going to be a weighted sum, and so I'll add into this variable. And so for every outcome and count in the hash table that goes between like the product and the number of ways to make that product, I will add into the expected value variable itself plus this new outcome times let's see here, times the probability of that outcome. So it's like the number of ways to make it over the total number of outcomes. And so that's how you calculate the weighted average. It'll tell me the total outcomes and then the expected value. So that's the idea. So the range, by the way, of x is here I am printing out the hash table. So it's like here is the range of everything. And let's see here. I'm printing it as I iterate through the hash table. So this is exactly what I just wrote, so it's all here. But let's go back to the slides now. So this is every key in the hash table, which is every possibility. So this is the range of the random variable, every different way to get a different every way to get a value after multiplying 2 dice together. whatever they read, that's the range. Like you could have got a 1 if they're both 1s. There's 2 ways to make a 2 because it could have been 2 times 1 or 1 times 2. And so on and so forth. There's one way to make 36 because that's 2 6s together. And then there's a few ways to make other things. So that's kind of cool. That's the range. And then here's all the ways to make that value. Here's the distribution. So that's the idea. So the range is everything on the left. Program helps. The distribution is here are all the ways to, like there's one way to generate a 1 by multiplying 2 dice values together. There's 2 ways to generate a 10. It could have been 5 times 2 or 2 times 5. Yeah. There's a few ways to make a 12. It's like 6 and 2 or 2 and 6 or 3 and 4 and 4 and 3. Things like that. There's 4 ways to make that, and that's a distribution. You can calculate probabilities from that, and that's exactly what I was doing with this expected value. Just what is, like, this is 1 over 36 times 1 plus 2 over 36 times 2 plus 2 over 36 times 3. This weighted average, that's how you calculate it. And that apparently gives us 12.25. So you can expect, on average, essentially, your random variable to have the value to 12.25. So when you roll your 2 dice and you multiply their values, you should expect to see the value 12.25 if you roll like a billion and you take the average of everything. Obviously, you can never get back exactly 12.25, but that's what it's tending towards. Okay? So that is a good example of expected value. A cool thing about expected value is if you have 2 random variables, or you just have 1 random variable, you can do cool stuff. You can do stuff that does not seem like you could do it, but it is all allowed. It's called the linearity of expectations that gives this to us. So if we have 2 random variables, for example, like the sum of the dice as well as the product of the dice or something, if we have 2 random variables defined on the same sample space, and then and C is like a scalar, C is a real number, then the following are both true. The expected value of the sum of those random variables, you don't have to calculate anything separately. It is going to be the sum of their expected values, which you already knew. And then finally, if you want to scale your random variable by some constant C, then you don't have to calculate the expected value of that any differently. The expected value of that scaled random variable is the same as the expected value of the original random variable. Just scale it. And so this is called the linearity of expectations. It's like you can distribute the expectation into every random variable, essentially. And like you can just deal with the expectations of the original random variables, which is probably easier to calculate. And here's a proof of the first one, like the expectation of x plus y is the same as the expectation of x plus the expectation of y. And this really saves you a lot of time when you prove things. And so what is this? How do you calculate the expectation of this big thing? Well, remember that x and y, they're just functions over the sample space. And so what is this but for every sample in the sample space, probability of that times the value of this sum random variable, which is like x at that thing plus y at that thing, whatever value those random variables are getting back for that particular event, that outcome, and then times its probability. So it's that weighted value probability. But this is just a normal addition, right? We can distribute the P of S into both of these, and so this is all the same still. It's like the summation of all this. That's still the same. That's equal. Then watch, you can separate. Like this could be one summation, just do over these things, and then make it another summation just over these things. It's like addition. You can do it in any order, so just split it up. Split it up into over the x's and over the y's. And then you're home free, because what is this by itself? But that's just e of x. What is this by itself? But that's just e of y. Isn't that cool? So that's the proof. You can just chain them together. It's really nice. Oh, and then here's the other one. I didn't see it originally. Sorry. So yeah, the C can be distributed over all this, and you can just leave it out, because all this is, again, using the definition, is probability of the sample times the value of the random variable. It's the C times the original thing. You can just bring that C outside. You can bring any constant outside of a summation, so you just put it there. And then keep the rest, and like this was the expectation of x by itself. Just multiply that by your C, and you're done, which is cool. And so you wouldn't expect that it's so easy to take smaller random variables and make a combined random variable and understand its expectation so simply. But that is all true. It's called the linearity of expectations. And here's a good example of that. Very helpful. So here's a problem, but let's make it a little easier on ourselves. Let's assume that the probability that a person is born on a given day is perfectly random and like there's no leap years or anything. So let's pretend that it's 1 over 365, which of course is not accurate. And then also, of course, there's leap years involved too. So it's even less accurate. But let's assume that the probability that somebody born on a given day is 1 over 365. And then the question is, in a group of 100 people, what is the expected number of pairs of people who have the same birthday? Okay. So this is a good example of the linearity of expectation. So first of all, we need to like eventually come up with a probability. So like we need to know what are all the different ways to do something. So it's going to be a combinatorics question, a counting question first. So like expected number of pairs of people who have the same birthday. So in total, like how many different pairs of people do we have in a group of 100? First of all, there are how many pairs of people in a group of 100? It's 100, choose 2. How many ways can you choose 2? Choose a set of 2 out of 100 people, where order doesn't matter. So it's just how many different ways are there to make a set of 2 people out of 100 people? So there's that many pairs of people, and that is that's equal to 100 times 99 over 2 factorial, which is just 2. And I did the math, and that's apparently 4950. There's that many pairs of people. And so there's a lot of different ways. Hopefully we'll have a few people with the same birthday, because there's a lot of different pairs that we can make. And the secret is, the way to do this using expected values and making random variables is, let's do this. Let's make, there's this many pairs of people, 4950 pairs of people. Let's make a random variable for each pair. Make the random variable P1, P2, P3. Let me draw it like that. So make 4,950 random variables and have them stand in for each pair of people, and every random variable needs a value. And so here's how we'll extract a number from each of these. Be random variables for each different pair of people. Random vars. So we have a lot of them. Random vars that take on the value 0 if this particular pair of people did not share a birthday. 0 if they did not share a birthday, but like make it a 1, make this random variable a 1 if this particular pair of people did share a birthday, which is interesting. Your random vars that are 0 if the pair, that particular pair number 4,949 or something, if that pair doesn't share a birthday, and 1 if they do. So like the first pair of people, maybe they do share a birthday. If so, make this random variable take on the number 1. If they don't, make the random variable take on the number 0. And so we have 4,950 random variables that are each all 0 or 1, depending. And what we care about is the expected number of pairs of people who have the same birthday. So we're after the expected value of the sum of all these random variables, because it's like it's a 1 if they do share, it's a 0 if they don't share. So that's what I care about. I want the expected value of the sum of all these random variables, because that'll give me the number of pairs of people that share a birthday expected. P4950. So I want this expected value. I know by linearity of expectations I can just give and add together the probability or the expected value of each, like just split them up. This is equal to the expected value of just the pair P1 plus the expected value of just the pair P2 plus all the way to the expected value of just the pair P4950. And all this is, these are all the same expected value, aren't they? Like, what's the expected value of a pair of people? The expected value of any of these pairs, Pi, well, it's gonna be, how do you calculate expected value? It's, all right, the value it could take on times the probability that it took on that value, the sum of all the ones. So this random variable could take on a 0, with the probability that it was a 0, with the probability this pair of people did not share a birthday. So if they didn't share a birthday, that means like one was born on one day and then one was born on a different day, so that second person was born on one of the other 364 days out of 365. So that's the weighted average if it's a 0. Or this expected value was a 1 with the probability that it ended up being a 1, which is they shared that birthday. There's a 1 in 365 chance that that happened. And so this is 0 times that plus 1 times this, which ends up being just 1 over 365. That is the expected answer. That's the expected value of this random variable. It's 1 over 365. Does that make sense? So bring together 365 people, 365 pairs of people, I guess, then you can expect for at least one. You expect one of those pairs to share a birthday, essentially. That's what it's saying. So the expected value of any pair of people is this. That's the weighted average. It's 1 over 365. And so these are all the same expected value. It's 4950 times this 1 over 365. So how many people in a group of 100 can I expect to share the same birthday? It's going to be about 13.6. I did that ahead of time. So a little over 13 people, almost maybe 14 people you can expect on average across a bunch of different runs of this experiment. And that's a very nice use of the linearity of expectations. I don't have to deal with this giant summation, or this giant sum of random variables and trying to calculate the expected value of all of that. I can just split it up, and that makes everything easier for me. All right? So that's the linearity of expectations example. And let's see here. I think I just have one main concept left. It's called the binomial distribution, and it has to do with experiments that have like a yes or no answer, like a binary thing, like it's a 1 or a 0, it's heads or tails, things like that. So that leads to the binomial distribution, and let's talk about it. There's some new terms, of course. I think this was all invented by this dude, Jacob, I think is his name. Something Bernoulli is his last name, and he's the dude who came up with this. And so we name this after him. So a Bernoulli trial is where you have an experiment and there's only two outcomes. Either there's a success or a failure. You declare one thing success and another thing failure, but there's two possibilities total. That's the idea. It's a binary kind of thing. So for example, like you flip a coin. Coin flipping. Because you can define like heads to be success and tails to be failure. Okay? And then we can talk about the distribution over the random variable defined by the number of successes. Like we want a successful experiment. We're going to run a bunch of different trials. We want to figure out the expected number of successes in a sequence of independent Bernoulli trials. Okay? Apparently, the distribution of that random variable is called the binomial distribution. That's how we've named everything. All right? So essentially what we're after is the probability of exactly k successes in a sequence of n independent Bernoulli trials, so like n coin flips. We want to figure out the probability of exactly k successes, so like exactly 2 heads when I flip 4 coins, something like that. And that gives us, there's actually a way to calculate that. Given that the probability of success is p, you know that ahead of time, and the probability of failure is q, and these are all independent, of course, so those never change. The probability of failure is, of course, the probability of the opposite of success, so it's 1 minus p. And so here is the probability that you can calculate. It's always, all right, I had k successes, so it's p to the k. They're all independent. I can multiply like that. I had n minus k failures, so I have to multiply the probability of failure. Right? I have to take the probability of failure to the power n minus k, just like that. So I had this many successes and this many failures. So you take their probabilities to those powers, and then, I mean, there's a bunch of different ways that you could have had k successes and n minus k failures. You have to multiply all the different ways that you could have had that happen. Okay, because essentially these outcomes could have come in anywhere. Like the successes could have happened all at the start and then the failures, or like the successes were interspersed between the failures. So for example, we would like to calculate the probability of flipping exactly 2 heads when we toss 4 coins. The way that you calculate that is, well, it's going to be, all right, I have 4 coins total. The number of successes I care about is 2. Let's say that heads is a success. So it's 4 choose 2 times the probability of flipping heads, so that's 0.5, of course, on a fair coin, at least. And how many times did I flip heads? Twice, so 0.5 squared. And then you multiply the probability of failure, so the probability of getting a tails, which is another 0.5, to the power of all the rest of the things. That's all right. If I had 2 heads and 4 experiments total, there's 2 more ways. I had to get 2 tails as well. Okay, so it's 2 heads and 2 tails. And I have to multiply this by all the different ways that I could have gotten 2 heads and 2 tails. Because there's a bunch of different options. There's 4, choose 2 of them. Let me show that to you. You could have gotten your heads first. Like it could have been, like the first 2 flips could have been heads, and then the next 2 could have been tails. Or it could have been tails, head, head, tail. Yeah. Or it could have been tail, tail, head, head. Or it could have been the heads weren't next to each other. It could have been heads, tails, tails, heads. It could have been heads, tails, heads, tails. It could have been tails, heads, tails, heads. You see that? There's a bunch of different ways to get 2 heads and 2 tails, and you have to keep track of that. But at the end of the day, they're all independent. So it's like this probability of heads squared, because I want 2 heads, and the probability of tails squared, because I want 2 tails to make 4 things total with 2 successes. All right? So that's that, and this is equal to 4 times 3 over 2 factorial, so 6, here are the 6, times, you can simplify that to 0.5 to the 4th power, and again, I did all the math ahead of time for ease. This is 0.375. So it's about a 38% chance that you're going to get 2 heads when you toss 4 coins, which is kind of nice. And so yeah, that's giving us, that's a probability, and you can use those probabilities to come up with an expected number of successes in n trials, so n coin flips. How many times should I expect to see a heads, for example? You do this kind of trick that we did over here, where you make a random variable and like you give it a 1 when it's a success, and you give it a 0 when it's a failure. And here's how you can calculate the expected number of successes for each trial. They're all independent of each other. It's like you make a random variable for each trial, and you make it 1 if it was a success, and a 0 if it was a failure. And the expected value of each trial's random variable is like the probability of success times a 1, because we want the random variable to be a 1 when it's successful, and then plus the probability of failure times the value of the random variable when it's failed, and that's going to be, we want it to be 0 when it fails. So that whole expression goes away, and we're left with just p times 1, which is p. And so the expected number of successes for a given Bernoulli trial is, for a random variable that represents a particular Bernoulli trial, that is exactly the probability of success. It's pretty nice. And so with linearity of expectations, you can, assuming you want n trials total, what's the expected number of successes? It's just, well, p for each thing, n total. It just distributes over that like that, so it's just n times p. And so, all right, if we go back to coins, for example, like I toss a bunch of coins, so the expected value of me tossing coin I, how many, and asking for success, how many successes could I expect to get every time I toss a coin? It's like 0.5 successes, 0.5 heads. See that? Because there's a 1/2 chance I get that heads. And then I can use this idea, this linearity of expectations, to figure out how many heads can I expect to see, how many successes can I expect if I toss 3 coins. It's just 3 times the expected value for a single coin. It's going to be, all right, you toss 3 coins, I can expect to see 1.5 heads. That's pretty much what's going on there. This idea comes from the linearity of expectations. It's like, all right, I have E, I'm trying to get the expected value of a certain number of trials times each individual random variable representing each trial. So that's C times just that original expectation of the original random variable, which for us is C times that probability of success. So that's the binomial distribution, and that's how you can use it to discover cool things. I would like you to try all that now with one last example. So I'll read this and then I'll show you this slide for a second and then let you try it. So, all right, here is a silly example. So we have a gambler, and that gambler has a coin which we're not sure if we trust the gambler, unfortunately. We know that the gambler has a coin which is either fair, like equal probability heads or tails, or the coin might be biased. The coin might be like a fake coin, a cheater coin, with a probability of heads equal to just 0.3 instead of the 0.5 that it should have been, right? So it tends towards tails if this gambler really has this biased coin. And we're not sure. We're not sure we trust him, but we ask him to flip the coin 10 times without knowing which one, like either he's using the fair one or the fake one. We ask him to flip that coin 10 times total, and we keep track of the number of heads and tails. And so my question is, if the number of heads is at least 4, you decide, like you think of this ahead of time, if the number of heads is at least 4, you conclude that the coin must have been fair. Like you set that up. That's like, I promise to believe you if I see at least 4 heads. If the number of heads is less than 4, you're going to go and conclude that this person's probably cheating you and that the coin was biased. So that's the setup. That's what's going on. And then what I want you to figure out now is, what is the probability that you reach an incorrect conclusion if the coin is fair? So that's what is the probability that the coin was fair and you said that it was fake. All right. So that means you must have seen less than 4, less than or equal to 3 heads, and you concluded it was fake, but it really was fair. So what's the probability of that happening? And then for B, what's the probability that you reach an incorrect conclusion if the coin is biased? So you really do see heads at least 4, so greater than or equal to 4 heads with the bad coin, with this coin that's unlikely to have done that. So what's the probability that you were wrong in each case? So see if you can figure that out. It has to do with the binomial distribution. See if you can get it. All right. So like here's the fair coin. Fair coin F has a probability of getting heads at 0.5, and then we have biased coin B has a probability of getting heads 0.3. 30% chance it rolls on heads. That's unfortunate. So what's the probability that we reach an incorrect conclusion if the coin is fair? So we saw less than 3 heads, less than or equal to 3 heads, sorry, but the coin was, and the coin was fair, okay? So what's like the probability of, all right, you can just add these all up. It's the probability of seeing 0 heads on a fair coin plus the probability of seeing 1 head with a fair coin plus the probability of seeing 2 heads with the fair coin only, because out of 10, right? 10 coin flips. Plus the probability of seeing 3 heads across 10 flips total. What's that probability? And then I think you can imagine that this is going to be very similar. But this is, all right, what's the probability that I see 0 heads given that it was the fair coin? All right, so we can do this. It's exactly this idea. It's like, all right, I saw, it's going to be 10 choose 0. I have 10 outcomes and 0 of them with heads times the probability of getting a heads, 0.5, and 0 of them, times the probability of getting tails, the opposite, Q, which is 1 minus the probability of the other thing, of success, to the power of the rest. So, and seeing 10 tails. So it's that plus, this time it's probability of seeing exactly 1 head across 10 coin flips. It's 10 choose, and I only saw 1. How many ways can I pick just 1 out of each 10? 10 rolls, and so then that's times 0.5 to the first power, because I saw 1 head, and then I saw 9 tails. So there's that, plus dot dot dot. All right, so that's that. And if you do the math, as I did before, it's 0.172. So there is a chance, there's like a 17%-ish chance that you were wrong when the coin was fair, but it's a low chance. All right, even though you saw under 4 heads, and you were wrong. It's possible, but unlikely. All right, and then the opposite is, what's the probability that we're incorrect if the coin is biased? So if we see more than or equal to 4 heads, because that's what caused us to conclude that it must have been a fair coin, but what if it still was biased? How would we tell? Well, that's another probability calculation. So it's like, all right, what's the probability that we saw, let's see, 4 heads exactly when this person flipped the bias coin? Add that to the probability that we saw 5 heads when this person flipped 10 iterations of the bias coin, because we're supposed to be wrong. It's the probability that we were wrong. Times plus the probability that we saw exactly 10 heads out of 10 coin flips of the biased coin that's hardly ever supposed to land on heads. What's the probability that any of these could have happened? So again, that's equal to like 10 choose 4 heads this time, times the probability of the heads, which is 0.3 this time. You see that? Times 4 successes, which is a head apparently. And then we have times the probability of failure, the probability of tails, which is 0.7 now. You see that? It's 1 minus 0.3 in this case, times the rest. And so there's 6 more rolls, and they must have all come up tails. And so if you add all those up, it apparently equals 0.35. So there's a decent chance, actually, that even though the coin is so unfair, it still might show up with more than or equal to 4 heads and cause you to incorrectly think that it was fair in 35% of the cases if the person rolled this dice, or not rolled this dice, but flipped this weird coin 10 times. Okay? So hopefully you see the logic there. It's an interesting little question. And yeah, please yell at me if you have any questions about any of that. And so with all this, we've come to the last slide of this deck of them. Let's try and bring this all back. This is about probability. Let's bring it back to computer science, something that we know and love, something that we care about. Let's talk about hashing, okay? Because remember, hashing is kind of dealing with probabilities. It's like, what's the probability that we're going to end up with like a bunch of collisions when we hash things? We'd like to spread it all out. So the goal of hashing is to make sure each bin that our number is hashed to, because it's just a big table, right? Just a big table mapping indices that are the result of like you hashing to this particular index value to a given maybe list of values if there's a bunch of collisions, right? There's a ton of these maybe. And it might go on forever. But all of these are supposed to be hopefully equally likely, all these different slots. So what we want all those to be equally likely, and we'd like to ask the question a lot of the time is, what is the probability of collision in a hash table with n slots, so n different places to put stuff, and m keys that I want to insert? And so we can calculate the probability of that, not too hard. It's going to be, well, it's easier to calculate the opposite. It's easier to calculate the probability that there are no collisions at all in this when we insert m keys into n slots. It's 1 minus that. And so what's the probability that there are no collisions? It's the probability that you insert the first key, there is no collisions, times the probability that you insert the second key, there's no collisions, times the probability that you insert the third key, there's no collisions, all the way to the probability that the nth key has no collisions. And we're trying to figure out maybe the worst case probability so we can deal with the best case of there are no collisions, maybe. Because 1 minus that will give us the worst case. We want the opposite. So in the best case, all the keys are random and each slot is equally likely. So let's assume that. So the probability that the first key has no collisions, it's just like, it's 1, because it's like there's n slots, or there's n places to put it and there's n slots. That's 1. And then the probability that the second key did not collide, it has to do with the first. Now there's n minus 1 slots that have not yet been filled over n slots total. You see how it's kind of going to go down like that? And then times the probability that the third key didn't collide. So there's n minus 2 slots that it could go now. What's the chance that it went to one of those rather than the other two that already have something in them? All the way down to n minus m plus 1 over n. And for example, if n is 2 to the 32, so like you have a few billion indices, and m is, you have this many, apparently, 77,000-ish keys to insert into your hash table, the odds of a collision, believe it or not, in a 32-bit hash table, like that's how many indices you have, is actually 1 in 2. This is like, there's a lot of slots to fill. It's kind of like the birthday paradox. But if you only insert 77,000 things into like a place with billions of slots, what? You get a 1 in 2 chance of collision. And this is what these paradoxical things that probability tells us, and we can watch out for now that we know it. All right, so we are unfortunately going to get a collision, pretty likely, but hopefully it's not going to get too full. And yeah, here's just a nice table that kind of displays all this stuff. If you have 64 bits for your hash table, so like your keys are 64-bit numbers, and so you have quite a lot of them, you would need to insert a few billion keys to get a 1 in 2 odds of seeing a collision. But the fewer numbers, the fewer things that you put into your hash table is going to give you a better chance. Like if you had 32 bits, so a few billion entries, and you only want to put in like 1,000 things, then you have a 1 in 10,000 chance of getting a hash collision. And so this is kind of what you can see here. And so here, like, we want to keep the probabilities low, and here are some funny probabilities, like odds of dying in a shark attack. That would be the odds of a hash collision if you had 64 bits of slots, 2 to the 64 slots, and you inserted a little over 500,000 things. The odds of a collision are just as good as dying in a shark attack, which is pretty good. So these are just fun things that you can calculate now that you know probability. And that is kind of where I want to leave you. You want to retain all this knowledge, even though it's mostly math, so that you can figure out cool stuff about the programs that you write. What's the odds that this happens? This thing that I don't want to have happen. What are the odds of it? And so probability can give that to you. And so that is the end of our slides on probability. And so I will see you in the next lecture.